Okay, we're going to do a calculation of area between some curves. This is from the supplemental textbook, Chapter 2, Section 1, Problem 15, where we are asked to find the area in between a couple of straight lines. One of them is slanting downwards. It's y equals 12 minus x, right there. One is horizontal at y equals 1, right there. One is y equals square root of x, which is the little curvy part. And they're not given in the problem, but it doesn't take long to figure them out. We have points of intersection between y equals 1 and y equals square root of x at x equals 1, and then between the straight line 12 minus x and square root of x at x equals 9. You can double check. When x is 9, this is 3. When x is 9, the square root function is 3. All is good. We need these points to delineate our integral. What we're going to do is do this problem in two different ways. And so one way is with respect to the x-axis. The area between two curves is just the integral of the curve that's above minus the curve that's below. In this picture, I'm going to use this as just sort of a pointer to sweep from left to right. When we're in this zone right here, the upper curve is 12 minus x, the lower curve is y equals 1. But when we get over here, the integral is bounded above by 12 minus x, but below by the square root function. And so I'm going to kind of delineate those two regions. Let's call them regions 1 and 2. The area that's the total of the whole thing, like so, is going to be area from region 1 plus area from region 2. And I need to write those separately again because the top and the bottom functions are different in each region. So for this region right here, we're hovering over x equals 0 to x equals 1. So on the interval from x equals 0 to x equals 1, the upper function is 12 minus x. The lower function is y equals 1, like so. And then for area 2, this time we're going to go from x equals 1 to x equals 9, like that. The upper function is still 12 minus x, but now the lower function is the square root of x. And there we go. Can tidy these up a little bit. Integral from 0 to 1, there's an 11 minus x dx plus an integral from 1 to 9. Well, yeah, that's not cleaning up very well. Like so. Okay, I'm actually not going to evaluate those integrals. I think these at this point we can call trivial. They're just either constants or powers. So it's a whole bunch of power rules. And then you're going to use the fundamental theorem to plug in the endpoints and subtract. So teacher's prerogative. I'm declaring that problem almost done. ... means there would still be work to do to get the actual value. What I want to do is do the same problem all over again, except with respect to the y-axis instead of the x-axis. Okay, we are ready to fire up this same problem again. This time we're going to do the integration with respect to the y-axis, which means we're going to be walking up and down this region right here. That's our baseline on the y-axis, and we're going to be looking out into the region and looking for the function that's, so to speak, above the other one and below. When we look out from the y-axis, you know, above means farther to the right. So for example, I need to split this region just like I did the previous example right there, because in this smaller region on the bottom, when I'm looking out from the y-axis, the top function, the function that's considered above, is that arc, and then below, well, it's just the y-axis itself. Up here, when we look out, well, now the straight line is above. In these cases, we are going to be integrating with respect to y, and we're going to make two integrals, like so. We just have to decide on endpoints, and what the functions are. So for the functions, we need to take the original versions y equals f of x and just flip them around so that they're x written as a function of y. So for example, y equals 12 minus x, just solve it for x, that becomes x equals 12 minus y. What was y equals square root of x becomes x equals y squared. And this curve actually just turns into one of the endpoints. There, I should write it as a total area like in the last part. Okay, so in this region right here, we have to decide what our endpoint is. Our lower endpoint is 1. Our upper endpoint, well, what the heck was that? Well, if you remember from the other one, that point of intersection between that upper straight line and the square root of x arc was at x equals 9. And since that's the intersection of these two, that comes along with a y value of 3. Up here is 12. So we're going to integrate from from y equals 1 to y equals 3, and then we're going to look out and find the function that's above, which is now x equals y squared minus, well, I guess we could put in minus 0 if we wanted to, but we don't necessarily need to. And then we're going to go up into the second section here. We're going to start from 3 and go to 12 on the y-axis. The function that's the above function is the straight line, which is now known as 12 minus y, and then the function below is just the axis. So again, if you want to put in the 0, that's fine. And then if we tidy this up, integral from 1 to 3 of y squared dy plus the integral from 3 to 12, 12 minus y dy, and that's it. And then if we went and actually calculated a value for this integral and calculated, well, I sneak this back in here, a value for the previous version that we did, we should get the same numbers back because it's the same area, right? You're measuring the area between the curves. And so whether we measure with respect to the x-axis like we did here, or whether we measure with respect to the y-axis like we did here, it's the same area, and so we need to get the same number back. So if you want to practice your integration, go do these and go do these and make sure you get the same answer. And if not, I did something wrong.